In this module, we start from a concrete business need, delivering legally binding, eIDAS-compliant remote signatures. Our aim is to turn that need into clear technical and compliance requirements that will later drive the HSM design, PKI structure, and deployment choices across the entire solution. A request for a remote qualified electronic signature service sounds like a single goal, but it actually hides three intertwined streams. One is how users will interact with the system day to day. Another is the quality of service the platform must deliver. The third is the set of legal and compliance rules that cannot be broken. Our job is to unpack that vague request along these streams, then rebuild it as concrete requirements, APIs and roles, latency targets, key protection levels, audit trails, and architectural patterns that we can implement, test, and later defend to regulators and auditors. To really understand eIDAS and HSM design, think in terms of value exchanged between four players. The end user expects a smooth, mobile-friendly signing flow that just works and doesn't feel like a security ceremony. The relying party, like a bank, mainly cares about strong evidence, signatures that are verifiable, hard to forge, and stand up in court. The QTSP has to turn this into reliable operations, resilient infrastructure, audited processes, and alignment with eIDAS and ETSI standards. Regulators and auditors finally demand proof, strict identification, secure key management, and cross-border recognition. A remote qualified electronic signature combines a simple user journey with a strict cryptographic pipeline. The user uploads a document and gives consent, while the system hashes the document so only a fixed fingerprint is ever handled by the HSM. Then, strong authentication verifies who is signing, and the engine binds that identity to secure session tokens. When the user approves, the HSM uses a qualified certificate's private key to sign the hash. The result is returned to the relying party together with the signed data, verification information, and an audit trail. Identity assurance is like a staircase you climb before you're allowed to create qualified electronic signatures. You begin by defining which identification methods you trust: national eID schemes, video identification, face-to-face checks, or bank-based KYC. That's your foundation. Next comes lifecycle management for that proof: how evidence is stored, how long you keep it, how you onboard, and how you revoke. Only after those steps can you reliably reach the high assurance level required by eIDAS, where strong authentication and an unbreakable link between person and signature are guaranteed. In an eIDAS-style signature service, every step leaves behind evidence. During enrollment, you capture identity data and link it to a future signer. Authentication logs then prove who actually accessed the service. At signing time, secure timestamps, signature attributes, and user consent records show what was agreed and when. Around this core, you collect contextual data such as IP addresses and admin actions that modified settings or keys. All of this must be logged with integrity protection, governed by clear retention rules, and exportable as structured audit reports for regulators and courts. For an eIDAS-ready signature service, interoperability is as important as security. Standard formats like XAIDs, KDs, and PAIDs ensure that signatures on XML, binary data, and PDFs can be validated by other tools and across borders. Their baseline profiles, such as BLT and BLTA, add the minimum metadata needed for long-term evidence. More advanced profiles extend this with trusted timestamps and validation data like OCSP or CRL references, so signatures remain verifiable years later. Real-world success then depends on clean integration with PDF viewers, XML and CMS workflows, and EU validation services. When you design an eIDAS signature service, you are really designing to a performance envelope. First comes latency. Users expect a document to be signed in roughly 2 to 3 seconds end-to-end. That budget includes identity checks, business logic, HSM calls, and network hops. Then comes throughput. You need a clear target for signatures per second or per minute at peak, because that drives HSM capacity, load balancing, and horizontal scaling. Finally, resilience. Plan for graceful degradation, queuing, rate limiting, and back off, so the service stays reliable even when it's overloaded or components fail. You are also balancing two envelopes: key protection and availability. On the protection side, regulators care that private keys never leave certified HSMs or QSCDs. that RSA or ECC keys are generated and stored securely, and that powerful operations require the right roles and dual control. On the availability side, business owners care about SLAs, RTO, and RPO, which drive choices like multi-region replication, clustering, and automated failover. Your architecture has to satisfy both sets of requirements at the same time, not trade one away for the other. Think of your eIDAS solution as a radar centered on hardware security. FIPS-validated HSMs give you a solid cryptographic core, but compliance actually lives in the surrounding layers. One layer is jurisdiction and privacy. GDPR principles like data minimization, pseudonymization, and strict data residency or EU-only processing. Cross-border transfers may require standard contractual clauses. Another layer is trust service specific. eIDAS QTSP obligations, conformity to ETSI standards such as EN 319-401, 411, and 421, plus ongoing surveillance audits. Design decisions must satisfy all these layers simultaneously. Addressing them one by one is not enough. To keep an HSM-backed eIDAS-aligned service continuously compliant, think in terms of 4 reinforcing practices. First, configuration control. Every change to HSMs, PKI, or supporting systems follows a formal change process, with documented approvals and rollback plans. Second, security assurance. You routinely test yourself through internal audits, vulnerability scans, and penetration tests, and you actually track and close remediation actions. Third, organizational controls. Separate duties so no single person can design, approve, and operate critical keys. And finally, evidentiary records. Retain logs, training records, test results, and incident reports so you can prove all of this to auditors. Here's how to read a requirements traceability matrix in practice. You start with a business need, like legal validity. You translate it into a concrete requirement, such as eIDAS qualified signature status, then anchor it to a specific technical control, like a FIPS 140 Level 3 HSM cluster. You repeat that pattern for scalability, privacy, and everything else. If you cannot point from a regulation to an implemented control, your architecture still isn't finished.